back on Mr. Murray's Mathland, and we're taking a look today at another free response classic topic on the AP exam, and that would be accumulation, but specifically the in and out rates type of problem. The snow is falling and snow is melting, something's being given, something's being taken away. Water's pouring into a tank, but it's also leaking out. People showing up at a theater, people, leaving the theater, that kind of thing. So we're going to take a look at all the sorts of classic questions that tend to come along with that, just to give you an idea of what to expect. So here we go. Here is today's problem here. We have the new math hip-hop TikTok star, Lil Calc. I got to keep myself amused here with these word problems. Going to be signing autographs at a local mall from 8 a.m. to 12 p.m. And 8 a.m. is represented by t equals 0, 12 is t equals 4. So we're only talking about that time interval, 0 to 4. People begin arriving at a rate modeled by a of t, 50 minus 9 times the cube root of t. And they receive their autographs at a rate modeled by r of t equals this, both measured in people per hour. So notice both of these are rates. They're rates. They don't, if you want to know how many people have arrived, you don't just plug a number into this. This gives you the rate. And we also are told this. I always want to read the question carefully. At 8 a.m. at time t equals 0, there are already 30 people standing in line. So people are going to start arriving, at this rate, but there's already a certain number of people there when you begin, and that's a common thing. There's already an initial amount of whatever it is you might be measuring. So part A says how many people arrive between t equals 0 and t equals 2. So always want to read these questions carefully. This just asks how many people have arrived. Not how many people have received the autograph, not how many people are still in line, just purely the total or accumulated number of people that have arrived. So whenever you're talking accumulation, that's really an integration kind of problem, a definite integral. And if I'm only caring about how many people have arrived between 0 and 2, then I'm just going to integrate the arrival rate. So a of t for shorthand, which is completely acceptable and encouraged, in fact, a little time saver rather than writing the equation. And we are going to approach this as if we have a calculator this whole time. So this, you could integrate this by hand and certainly do it, but let's get good with some of these calculator tricks as well. So I've already put these in y1 and y2. y1 is where I've put the arriving, y2 is where I get the receiving rate, people leaving. And I've already set the windows on my x-axis, since we're only going from 0 to 4. That's a definite good thing, 0 to 4, to set your windows at that particular interval so you're not looking at a broader range and you fool yourself into thinking about behaviors that aren't really there. And the y min and max is not always an easy thing to figure, but I went from basically 0 to 100, or -5 to 100, and this gives you this picture of the graph. But a of t is in y1. So when I want to know 0 to 2, that integral, I'm going to go math 9 and 0 to 2, set those limits of integration. My integrand is what's in y1, so I'm going to use the shortcut here, alpha trace, to bring up y1, or you could certainly type the equation. And with respect to x, you're always using x regardless of whether it's t or whatever on paper, and then hit enter. Let the calculator do the work, and it says round to the nearest whole number, which we'll often say for things like measuring people. But if it doesn't say that, remember, always be accurate to 3 decimal places. So this rounds to about 83 people. If you want to be specific, people have arrived over that interval 0 to 2. Okay, and remember, anything you use your calculator for is great. You just have to show some proper notation. You know, if you don't show this integral and you give the 83, that's what they call a bald answer, and you will not receive credit for it. But just showing that makes all the difference. Okay, so that's a classic sort of part A to these kinds of problems. Let's move on. Part B, going to take it up a notch, I'm sure, do a few more things. Now, part B, how many people are in line at 11 a.m. or t equals 3? So now here's where you're taking into consideration all three things. One, how many people were there initially? Two, how many people have arrived between that, 0 and 3? But also, people are receiving their autographs and leaving the line. So you have to take away how many people have received it. So here we go. This is basically, we're going to start with the 30, and we're going to add on to that between 0 and 3, right? Because it's from 8 a.m. That doesn't need to be specified, from t equals 0 to this time of 3. How many people have arrived? And then I'm going to also take away how many people have received their autograph, because they're leaving the line. And this could be done with a separate integral, or I could just tie it in as one big integral, a of t minus e of t. It's the same time interval from 0 to 3. Make sure you have that differential on the end of dt. And there we go. That is all I need to show on paper. And now we'll let the calculator do the rest of the work here. So here we go. 30 plus math, 9 for function integrate, going 0 to 3. And alpha trace, that's my y1, minus alpha trace y2 with respect to x. And go ahead, Mr. TI, do your work. Okay, and so to the nearest whole number, that would be about 44 people in line at 11 a.m. Okay. Part C. At 9 a.m., aka t equals 1, is the length of the line increasing or decreasing at that moment? So we're not asking about how many people are in line, just is it getting longer or getting shorter at that moment? And when you're doing that, you're really just comparing the two rates. Basically, are more people arriving at that moment, or are more people leaving at that moment? Which one is a greater value? And so there's any number of ways to illustrate this, but here's even a nice visual, which will tie into, how we're going to do part D. But take a look at this graph. The blue graph is the arrival rate, and the red graph is the receiving rate. Notice for this whole chunk of time, up until those two graphs intersect, the blue graph is greater than the red graph. That means people are arriving at a faster rate than they're receiving their autograph. So that would mean the entire line is getting longer if people are showing up at a faster rate than they're getting served. But after that point, people are receiving their autograph, they're getting served faster than they're showing up. And that would, yield an overall decrease in the line. The line would start to get shorter. So at t equals 1, you can really just see on the graph here, but at t equals 1, the blue graph is greater than the red graph. So more people are arriving than are being served. That means the line is increasing in length. And so to get that point across, you could do any number of things. You could find the two values individually and then just, say it. You could, and so I think that's what I'll do. I'll just show that a of 1, since I've already plugged this in, a of 1 is 41. And the other one, r of 1, And so when you want to switch the other graph, you hit up or down. That switches between the two. And R of 1 is 11.413. And then you just have to, you don't want to leave it to the grader to guess. You want to make it clear that you really know what you're talking about. So since A of 1 is greater than R of 1, the line is increasing. In length. And there we go. All kinds of things you could do. You could also show, A of 1 minus R of 1, that sort of thing we did, and you would get a positive value from that, basically showing that the difference between these is still a positive, so still yielding an overall increase. But that's really just the same thing as comparing their two individual rates. But a few different ways to get that across. And now let's take a look at part D here, which is, usually a question that's asked along with one of these, is talking about when that overall amount is a maximum or a minimum. In this case, find the number of people standing in line at the time when the length of the line is a maximum. So I need to first find when the length of the line is a maximum, and the ultimate answer to it is how many people are in line. Basically, what's the longest the line ever gets. And notice this is a closed interval, and it doesn't use the word absolute, but we are referring to when is this an absolute maximum, the biggest. So don't forget, you need to consider the endpoint values. So whenever you're talking about an absolute or a global maximum or minimum, so I'm going to assign a name. So I'm going to let L of t equal total number of people in line. And sometimes this is handy because that way you have a name to give it. And I've already basically established how to do this in a previous problem, but L of t is always going to be, and it's nice to do this because also sometimes this might be a part of a question. It might just be like create a function that describes the total number of people in line, and so it's a good exercise here. You would be taking your initial amount that were there, 30, and adding on from 0 to whatever time you are curious about the total number of people that have arrived. Now watch this though. This is frequently a thing. Notice I used A of x minus how many people have received it. So minus R of x dx. And that's a common thing, that if you're creating a function and they're dictating that you use time, if they didn't tell me to do this, I'm doing it kind of on my own. And so that time would be this, limit of integration. You can't use the same variable here. So you just have to change this to a dummy variable, some other variable. X, why not? But it couldn't be the same one, because that way if you were doing, say, L of 3, you would really be referring to putting 3 here, not putting it here and there. And if you use t, then that's what you would be saying, and then it just wouldn't make sense. So if you use a variable here, you got to change these variables. That's the big point. Okay, so how to get this across and do it kind of efficiently without, spending too much time on this is I like to present it as a table. It doesn't have to be presented that way, but now that I have L of t defined, I can sort of use that in my table, that I definitely want to consider 0. I definitely want to consider 4, the two endpoints, but you also want to consider any critical points in there. And the critical points are when those two graphs are equal. We've kind of said it before, but before that intersection point, the one graph was greater than the other. And then after that, they swap places, and then they're being removed at a faster rate than they're showing up. Well, right where they intersected was the longest it ever was going to be, right? Something changed. So You always want to find that value, but by doing an intersection between the two rates. But remember, anything I do with my calculator, I need to show on paper. So critical numbers is really just saying, when does a of t or a of x equal r of t? One of those two rates equal, and now I'll get the intersection. But remember, solving an intersection is really solving an equation, so you've got to give the equation you're solving first. So how to find an intersection, hopefully that's pretty common to you at this point, but second trace, intersect, and there's only one here, but if there was more than one, you would just want to move the cursor closest to that. It's always going to go to the closest intersection. So enter, 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 since it was the only one here, and they intersect when t is approximately 1.710. And as far as what you write on paper, I'm writing 3 places, but since I'm going to use that to get the length of the line, I might not want to round. I would either want to write more decimal places here, because I'm going to use it to get L of t, and if you use a rounded value, then your answer might not be as accurate. You can also use this feature here, which is sometimes handy. I'm going to bring back the last thing I found, which is the answer feature. That will always bring back the last thing you calculated, which, notice, is that intersection value, and it uses the full decimal, and I'm going to store it. Suppose this were a problem where I needed to use it multiple times, like over and over again. I'm going to store it in one of my letters, A, B, C, D, E, wherever you want. I'm going to store it in A. So you store alpha, pick whatever letter you want. And now, anytime I want to use that full decimal value, I could just put the letter A. Okay, so now actually getting these values from the table. At 0, I know how many people were there. It was 30. I don't really need to do any calculating. To get the number of people at 1.710. And notice, see, I don't have to write a new equation to get this value, because I've set up a table where I've named the function and I've defined what the function is. So by me writing this, that's the same thing as me writing out a new expression for it. So, and in fact, if you've already used your calculator to do this previously, I just did it at t equals 3. I could just go back and change that number from 3 to 1.710, etc., or A. These are little tricks, so you don't have to retype things over and over again. That could save you a valuable minute or two. But sometimes that adds up on, when you get to the end of the AP exam. You need every minute you can. And so now I'll round these answers to the nearest whole number. Although it didn't specify to, but I'm sure it would. I made up this problem. But you get 80.492. Didn't specify to, so I won't round. I didn't specify to. And then lastly, how many are there at the end? And so second enter, I'll bring back the last thing I typed, and I'll just change that A to a 4. And so we get about 16.179. So, no mystery here, no surprises that the longest the line ever was at this intersection value of 1.710, because after that we can see on the graph the receiving rate was greater than the arrival rate. So that would mean the line is getting shorter and shorter. But notice it never got down to 0. It didn't make up that difference all the way. So I guess there's a few people who didn't get little calcs autograph. So sad. So let's just actually answer the question. Never forget to do that. The number of people standing in line. So the max number of people in line is, and again, they didn't specify to round, or I didn't remember to include it in my directions, round to the nearest whole number. So I'll use 3 decimals, trying to be formal, 80.492 people. And sometimes I like to include, just to cover myself, which occurs at t equals 1.710 hours. So there's sort of the final answer, and you've kind of answered the question in full there, maybe even a little extra, but you got yourself covered either way. Okay, so those are a lot of the major ideas, along with some calculator tricks to help it go smoothly. So hopefully this reviewed a lot of little ideas there. And if you have any questions, as always, just ask. There's lots of other similar but interesting variations on this that the AP has released over the years. So if you're looking to see more examples, check them out yourself or just ask me for some recommendations. All right, keep working hard, kids.